Martin.
Stand over here.
I'm intrigued. I know what you're going to do, but I do like Martin's presentation. So let's welcome Martin.
Right, thank you. So hi, I'm Martin. I'm going to talk about are FPGAs unique for security. This title was inspired by a statement in the call for papers, which was a suggestion of talking about why FPGAs are unique for security. Those of you who know me will, it's as high as it goes. Should I talk louder? That's all right. Yeah, so I am usually wound up by statements of we are special. I come from automotive. We thought we were special. I don't think we are that special. We have the same security problems as everyone else. So that's what triggered that. Apparently, I've gone on a few slides. So to try and persuade you that I might have something useful to say, I have quite a lot of history with FPGAs. I started electronics when I was 8. I did an electronic engineering degree, and I've then worked for Lucas and TRW and ZF through a series of mergers. I spent a bunch of time doing FPGA work there, including some image processing with a 98% full FPGA, which was interesting. And I also did the security architecture for a radar FPGA-based image processing system. And then about 10 years ago, I moved into a much more full-time security role, building a penetration testing team within ZF. Which operates as a consultancy. So we do pen testing of ZF products and for external people as well. And we still do system design consultancy in the security space as well. Why is it going on? Oh, I'm going to have to keep an eye on that. Draw your hand. And a few years ago, I started a part-time PhD looking at weird side channels in embedded systems while I carry on doing my ZF work. So we're going to do FPGAs and uniqueness and security. We need some definitions. What is an FPGA? It's got some field customizable logic in there. It may have processors, it may have software, but it has to have some logic. Why does it keep going? No. Oh, have you got that on? Ah. Yeah, but I didn't want them in there. They must have stayed in there. Right, I'll keep an eye. I'm obviously going too slowly. So security is defined in a traditional InfoSec sense, confidentiality, integrity, and availability. You don't want your colleagues to read your payslip. The company doesn't want you to modify your payslip so you get paid more, and you need your payslip when the Inland Revenue come calling. So I've gone on 3 slides now. Exciting. You have an embedded system. We want to maintain the integrity of that embedded system. If it's doing safety critical actuation, you want to make sure that it doesn't actuate when it shouldn't do. If you're keeping someone else's data confidential, you need to maintain that. In order to do that, you need to maintain the security in the CIA sense of your firmware, your keys, the user data, those kind of sub-assets within your system. What do we mean by firmware in this context? Anything that can be changed easily or changed in some fashion in the field. So the actual software, configuration data, file systems, gateware, bit streams, whatever you'd like to call them. And then let's talk about what it's unique in comparison to. So maybe a board full of logic gates, but as this is an FPGA conference, we'll not talk about that. Smart cards, general purpose embedded microcontrollers, and server-based computers all have their own trusted entities within them. They all have a common set of problems. You'll need a debug port. Talked about that already this morning. Engineering development interfaces. There's this tension between whether you can debug this thing in the field and whether that's secure if you actually allow that feature to take place. You've usually got some kind of network connection, and often there's external memory, flash, or volatile memory as well. The basics are these cybersecurity goals of maintaining the integrity of your product so that it acts in the way that you want it to. It does the safety critical thing that you do. It's a missile, it does the unsafe thing that it's designed to do to the right people. The security of any data being handled, whatever product you are supposed to be doing needs to maintain that. And so you need to maintain the integrity of your firmware and the confidentiality of your firmware. Even if you don't think there's significant IP in your firmware, most vulnerabilities come about because somebody got the firmware and found a bug in it. So you want to keep the firmware confidential anyway. Why attackers are doing things. It's very dependent on what your product is. It may not have a financial motivation, but they might want to enable some features like heated seats in their BMW without paying for them. They may disable some of the security features like the immobilizer or the door locks or whatever else you have. Or there are just other assets like the keys within your system, the software, or your IP address. They might just want to put your webcam onto a they might just want to get hold of your IP address to form part of a botnet, or they might just want to show off. They want to publish some research. See if I can get through this one in the appropriate amount of time. There's a lot of attack surface on systems. Yeah, if you've got connection to the internet, you've got a cellular interface. People from all over the world can attack you. If they're nearby and you've got a Bluetooth or Wi-Fi interface, or they might try and influence the GPS system so that you look like you're in a different place to where you actually are. They can get access to the outside of your box and then access the UART or the Ethernet interface. Then they go inside the box, and there's all sorts of things. There's internal debug ports. There's SPI that you can manipulate or extract the data from, swap chips, clone the devices. There are power side channels and glitch attacks that we talked about earlier. There are some weird attacks on DRAM chips, which allow you to manipulate the data just by accessing other data, or you can break Intel's confidential computing by tweaking how the RAM is connected. All sorts of weird things go on there. And then you've got firmware, all the sorts of firmware problems. QNX, whatever your RTOS is, will have bugs in it. Your code will have bugs in it. And there are some FPGA-specific things. So you can make your FPGA overheat. You can make data leak on the internal lines of the FPGA. There are a couple of ones up at the top, Starbleed and Just Start, which we'll talk about, which are very specific FPGA bugs. And there are HDL coding issues, which the box is further down, you'd be able to see. So there's a whole load of stuff you've got in defenses. We talked about a lot of that this morning, even TRNGs on that board. But there are some specific things in FPGAs which are of interest. So side channel mitigations are not common in traditional microcontrollers or in server-based processors. Having a triply redundant security micro is very good for defending against glitch attacks, and there are FPGAs with that kind of thing in place. And the sort of mitigations where you can throw keys away because somebody's been nasty to you, that's often not available to conventional micros as well, but there are a lot of those in FPGAs. So let's look at some attack paths. This is going to be fun. Okay, so starting with the intellectual property and your low-level firmware. People want to read it, people want to modify it. Securing the JTAG port, always a good start, also mentioned this morning. But people will still be able to read the firmware from your external flash chip and they'll modify it in there. So we've introduced firmware encryption and firmware HMACs. Those are good, but differential power analysis allows you to get around the encryption, and the Starbleed vulnerability allows you to get around encryption and the HMAC problem. The only real mitigation to Starbleed is to have a device that doesn't have that in it. And the newer devices have signed firmware in there, which mitigates that problem. Also mitigates differential power analysis because you can force the attacker to use the same bit stream over and over again because they can't sign one, and therefore you won't try and decrypt it before it's been checked. And you can also introduce rolling keys, which mean that the attacker only gets a very small amount of data for each key, which makes DPA much harder to do. So we've got integrity enforced by the signed firmware. A cryptographically relevant quantum computer will be on the way at some point, and that will break that. We'll have to start using post-quantum cryptography to mitigate that issue. Glitch attacks are still a problem. There are glitch attacks on the RSA authentication, but the triple mode redundant logic helps with that. And there is the Just Start vulnerability, which applies to a specific set of chips. If you enforce the encryption, then that goes away. So that's all of that in one place. Only 2 of those are actually FPGA specific. The rest of that applies to all sorts of different chips. So Starbleed, this applies to a very specific subset of one vendor's chips. The bitstream encryption uses AES in CBC mode, which has an interesting feature where you can tweak a bit here and it will flip a bit here. And you can use that to manipulate the bit stream so that you can read a word of the decrypted bit stream, put it into a special register. The WB star register has the magic capability that it doesn't get cleared when you restart the FPGA. So you tweak the bit stream, you send it in, the FPGA notices it's a rubbish bit stream and reboots. That's an availability measure. We don't want to stop booting, but the attacker can then read that WB star register. They've got a 32-bit word out of the bit stream. They can then tweak the bit stream again, do it again and again, and eventually they have the whole bit stream. And the bit stream includes the HMAC key, which is what protects the integrity of the firmware. And so they can then start to manipulate firmware to their own liking. Fundamentally, the commands were interpreted before they were validated. So the commands are attacker controlled. Later chips do the RSA validation of that and also use CTR mode of AES, which doesn't have the same bit flipping vulnerability within it. So Just Start is one that's followed on. The attackers fuzzed, well, they were researchers, they fuzzed the configuration engine and found not only that the previous one exists, but there are other ways of doing it which might be more efficient as well, but also that they can bypass this this flow of checking whether the FPGA is in a good state. So what normally happens is that you write the header and footer into a buffer, the bit stream is written into the FPGA, and it has to go into the usual location where it executes from, because there isn't anywhere else to store it. So the unencrypted good or bad bit stream is in the FPGA, ready to be checked. Then you send this RDW go command, which verifies the header and the footer and the bit stream. And if it's good, it executes the footer, which starts the FPGA up. And if it's bad, then the FPGA blocks. But they notice that if instead they don't send the RDW go, they just send the normal startup sequence, the FPGA is quite happy. And it will take the bit stream that you've already put in there, not try and validate it, and just run it. Just start. The mitigation for that is to enforce the encryption. If you do that, then what gets written into the fabric of the FPGA is the bit stream that's encrypted, just a random set of noughts and ones. When you try and start the FPGA, it has no idea what to do. It will do something random, but the random thing is just usually nothing at all. So that is so far the only mitigation to that vulnerability. So looking at your data at runtime, you want to maintain the confidentiality of that. Power analysis is still an attack that's appropriate. So DPA not only applies to FPGA, to the bitstream confidentiality, but also the data you have in your system. There are standard leakage defenses, masking of cryptographic operations, introducing random noise, making sure the timing is variable can all help with that. And then the FPGA specific one of timing leakage on adjacent wires, which we'll just go on to. So the attacker model here is that they've created a malicious IP core, and they're going to take advantage of the fact that one of the long wires on the FPGA, if you build a ring oscillator around that wire, the frequency of that will depend on the logic value of an adjacent wire, even if that's a static naught or a static one. That will change. You can see on the graph there is a small change in the frequency of the ring oscillator, and they built systems which are therefore able to extract the Hamming weight of key information, and from that they could actually exfiltrate keys from across the domain from the attacker side to the victim side. If you reserve some long wires in your FPGA, so you effectively move the attacker and the victim apart, you can mitigate that problem. And I know that Xilinx AMD have got some tools for doing red-black isolation. I don't know if other people have as well. Is that a thing Microchip have in their tools? Yeah, excellent. The answer is yes. Yeah, so you have to separate out the secret bits from the potentially attacker control bits. A couple more attack paths. So at the top right, we've got cloning attacks, which you can use physically unclonable functions or unique IDs to link parts of the system together. I'll not go into this in detail, but the link at the bottom is well worth a watch. This group of researchers managed to effectively take offline a bunch of cloud FPGAs by sending bit streams to them, which created very, very dense hotspots within the device, which is entertaining. And the guy who presents it is very entertaining as well. Let's talk about HTL code troubles. So the whole load of stuff on the left-hand side, which is from the common weaknesses enumeration. They're software problems. Everyone has software problems. But there are a couple of things that might be a bit more FPGA specific in terms of surprising default behavior and simulation and synthesis mismatches. So we have a secure write-only slave. I've made this up, so this is not real, but it could really happen. And we use the prot signal, which is halfway down on the left-hand side, to signify whether this is a secure transaction or not. And 0 means secure in Axie land, which surprised me, but that's how it is. And so that's decoded. On the right-hand side, we've got this allow write instruction, wiring, which the rest of the slave uses to decide whether it's a secure transaction or not. So when we instantiate that, we have a top-level module on the left. We've got a bunch of state machine stuff I've made up. We've got our instantiation of the Axie slave on the right-hand side, which has a bug in it. Don't know if anyone can see it. Part of the problem is, in amongst all that code, it's quite difficult. But there we are. The AW prop line has been missed out. Maybe you copy and pasted that code from somewhere. It just got deleted or something. And it got replaced by a blank line, which will then default to all zeros, which is secure and privileged for every transaction. There'll be a warning about that somewhere in your million-line long log file. But yeah, that could easily get out. Let's be even-handed, some VHDL instead of Verilog this time. There's a state machine, it has 3 states. The 3 states are all enumerated carefully. So there's a when others clause, which the synthesizer says, I don't need that, all the states are covered. Then the implementation engine takes that and turns it into a one-hot 3-bit binary. So open is 100, and locked is 010, and startup is 001, and then there's a whole bunch of other state machine values which are invalid. It'd be nice to have an others clause to cover those and get something sensible done if we ended up in one of those invalid values. But that's been thrown away by the synthesizer. So now you've got a bunch of logic where you thought you'd protected against it, but now you've got invalid values which can be hit, and you don't know what they're going to do after that. You can put pragmas in place and constraints to actually mitigate that problem, but it's really quite hard to check that you've done it in all the appropriate places whilst not inflicting the growth of logic that would put on the rest of your system. This one. So I don't know if we've ever left over some debug code in our systems. No. We've disabled the security by commenting out this bit of code here just for synthesis. So in simulation, that code's still in there and all the tests pass, management are happy, green lights all the way. But we've commented it out because when we're debugging it on the bench, the security really gets in the way. And so, yeah, if you forget to remove that bit of code, you will end up with your system fielded with the security disabled, and probably nobody checks that the security actually works in the field. They just check it in the simulation. So are FPGAs unique security? Mostly no. I think most of it happens across all sorts of software and other embedded type systems. They're all got to deal with confidentiality, integrity, freshness of their firmware. Most of them are internet facing or network facing of some sort. You have a debug port, you've got external memory devices. The impacts are either safety or integrity of someone's data, or something leaks, or your device gets abused into a botnet. There's a whole common set of controls that we use across all of those things. There are some device-specific attacks. We've seen some of them FPGA related today. but they all have them. There's a whole bunch of secure boot attacks or glitch attacks, and there's things that are very device specific across all industries. And there are standard coding errors. CWE is full of them. And they're things that really do differentiate FPGAs a little bit. I think the level of mitigations against power side channels is not common in standard embedded parts. The understanding that that is a valid attack and that's documented in the public documentation. The public level of documentation is much higher in FPGA land. And I think simulation and synthesis mismatches are not common across embedded systems. Running simulations on a different architecture to what you're actually going to end up on is not that common. So what do we do about it? Everyone should be signing their software updates and disabling the engineering features and the debug ports and things, authenticating the network connections. We haven't really talked about that, but pinning your TLS certificates is something that pen testers really like to inject their own TLS certificates. And if you're not protecting against that, you will just get completely wrecked. Design your security architecture so that your secret keys can leak and it doesn't catastrophically break everything, because they will at some point. And it's about time everyone needs to evaluate the risk of a cryptographically relevant quantum computer, which may break all the asymmetric crypto we have going. Most people probably should use a symmetric authenticated boot with an encrypted flash chip and enforce that encryption, because not only does it help against the just start bug, but it makes the attacker's life much more difficult if they can't just use their own bit streams. If they have to, if all they can do is do random things by putting a bit stream in and it being treated as encrypted, it makes life much harder. And think about where you're going to put your National Cybersecurity Center approved quantum safe cryptography, so that when a quantum computer comes along that can break things, you are in a position to do something about it. And some devices at the more extreme end, using asymmetric authenticated boot can be helpful, really considering the true risks of what power side channels can do to you. So you can mitigate that with device unique keys and rolling encryption keys. Using glitch hardened comparisons and glitch hardened cryptography as well becomes important when you're really trying to get it going well. And the risk of attacks on DRAM, there's quite a lot of research into DRAM attacks at the moment. And actually just implement some of that post-quantum cryptography. So there we are. I haven't had the marketing slide because we are a consultancy. You need help with any of that kind of thing, whether it's FPGAs or not, yeah, give me a shout. Scan the thing for the product catalog. That's me. Thank you.
You can't put QR code in slides.
Yeah, anyone who
So
scans the
anybody
QR
spot the
code.
security flaw in the slide? Right, Peter's got a question. There you go.
Sorry to labour the point, but I really like the what to do slide, because that is the basis for the Tara.
Yes, it's basically what comes out of most Taras is
Exactly that.
Yeah.
So that's a really feeds into everything else.
Yeah.
The one question that I've actually got is, looking at what you've actually said, I guess that it's all related, or most of it is related to the SRAM based architectures. Is it only Xilinx that you did this evaluation on?
So Xilinx is where I have most experience, but I was trying not to be particularly focused on a particular vendor.
But it is the SRAM based.
But a lot of the stuff I've mentioned is because you have an external flash device. Yeah.
Right.
If you don't have an external flash device, and that applies to a lot of the products that my company makes, things become much easier because your code is not exposed to the outside world in anything like the same way. And so, yes, a flash-based FPGA has, I think, probably just fewer problems.
A lot fewer problems.
Yeah.
But anyway,
Yeah.
moving on.
Yeah. Yeah.
Where?
No, he's not allowed to ask questions.
With your simulation question, isn't it analogous to compilation and optimization within a software tool chain? So the FPGA toolchain itself will optimize for the simulation and the generation of the gates. So are there any lessons learned that you think should be carried across into the room from there?
Certainly, yes, there can be optimizations in the software domain. Memory clearing is a classic one where you clear some memory, the compiler says, oh, you don't need to clear that memory because you're never using it again, and then optimizes that way. State machines also have similar sorts of issues as well. Yeah, and I think that as we move to pushing more testing into a sort of PC-based environment where you run lots and lots of tests on individual parts of your code in a PC and then bring the whole thing together and push it onto an embedded system, there's likely to be a bunch of if-defs in your C code which say if-def Intel do this, if-def NXP do that. And those are opportunities for, yeah, architectural-based things to go wrong. Yes, yeah, there should be a closed loop, which means you will find those things. I can imagine that doesn't always happen. Any more?
You said about debug ports. CRA requires for crypto agility and for updates and for so on and so forth. Doesn't necessarily have to be done through the debug port. Could be done through protocols and other interfaces. Do you see any problems in tying those together or separating those?
I think debug ports are orthogonal to updates, but if there's some kind of cryptography involved in that debug port unlock, and that is hardened, then that may be a problem that you can't fix when a cryptographically relevant quantum computer comes along. If you're doing some kind of RSA key exchange when you connect, you won't be able to fix that. And that's the kind of thing that on the left-hand side of the what you should do slide, you need to consider all of those things at this stage so that you know what risks you are. Maybe not cybersecurity risks, maybe just the business risk that if this kind of quantum computer comes along, our product is no longer valid. Okay.
In the chat.